Okay, this is the review for the third midterm. Um, as usual, it's on all 3 days of the week in class period of week 13, immediately before Thanksgiving. Sorry about that, but that's when it fits in. And as usual, one click if you have a problem getting it in. If you internet goes down, then screenshot or timestamp a screen capture and send it over for me. Material covered is on the energy equation, week 8, dimensional analysis including Buckingham pi, week 9, and the pipe flow material from weeks 10 and 11, except it excludes networks. It includes individual pipes, but not parallel or series networks. There are 3 questions, one on each of the days. Monday and Friday are rather similar in that they are pipe flow using the energy equation, and Wednesday is typical Buckingham pi equation. We've had those in the past, and you can see exactly what those look like. So in terms of summarizing material for the weeks 8 through 11, week 8 was the energy equation, and so you know that that is using basically Bernoulli between an upstream location and a downstream location. They have to be upstream and downstream for the pump head to be positive if it's input energy as a pump, or negative if it's recovered energy as a turbine. And the head losses are always positive. The head losses importantly scale with the velocities in the fitting. So in this reservoir system, the large reservoir assumption is that the upstream and downstream reservoirs would have zero velocities. So these terms here would go to zero. But the term that is taken up in the head loss term, the velocity term, is non-zero because it's actually in the fitting, so to speak. And of course the flow rate for the pump head, which is defined by this expression here. This is the flow rate here, volumetric flow rate, density, and gravity. And this would be the power in joules per second or watts. So this, importantly, this flow rate, Q, is equal to the velocity times the cross-sectional area. This flow rate is not equal to the zero of the pump of the reservoirs. So that's important. The physical meaning of this, of course, is that the elevation and pressure heads and velocity heads are summed to each other. So the Bernoulli head, if you like, at this point is equal to this, the sum of the elevation, velocity, and pressure heads. The velocity head, if it's a pipe that doesn't change in diameter over its length or area, cross-sectional area, will be the same. And the meaning of the pump heads is pump head is its energy in. If you have a turbine in the system, it's energy out, and the head loss is something that makes the grade line different from horizontal. So the usual energy grade line would be horizontal. The fact that it has a head loss in it means that you're losing energy in the system as it flows from upstream to downstream. So that's the energy equation that we would use. You don't need the other one that's written in terms of enthalpies in this particular test, neither on Monday or on Friday. For the individual components of this, the pump heads we've described already. It's positive if it's a pump, it's negative if it's a turbine. This has to be in the same units as these other components, so it's in units of length. The head losses are also obviously in units of length, and it's defined either in terms of a minor loss if it's in a fitting, where it's really the sum, I guess it's the sum of these head losses. It's the sum of these head losses multiplied by the velocity in the fitting, or if it's within a pipe, it's the velocity of flow within the pipe, the length of the pipe, the diameter of the pipe, and the friction factor, which is the equivalent of this parameter here. These are both non-dimensional parameters that scale the magnitude of the head loss as a function of the departure from zero loss. If you have a pump in the system, you can calculate the pump head that you have. It's a function of the power, the mass flow rate, and the gravitational acceleration. The mass flow rate you can also write as a product between the density and the volumetric flow rate, meters cubed per second times kilograms per meters cubed. And of course, the volumetric flow rate you can define in terms of the velocity of flow applied uniformly over a cross-sectional area of the pipe. So in terms of this equation, when we look at flows within pipes, we look at the friction factor as being a function of the length of the pipe divided by diameter. This is obviously non-dimensional. This is units of length. This is units of length, and therefore by definition this must be dimensionless, as we've said. And these friction factors, essentially for pipes, fall into these two categories. If it's laminar, then the friction factor is a function of Reynolds number. In other words, as Reynolds number changes, the magnitude of this friction factor decreases as the Reynolds number increases. And for turbulent flow, the friction factor is independent of the magnitude of viscosity. And so this is really explained in the idea that in laminar flow, the velocity distribution within the pipe is this parabolic velocity field, and will always look like this. But when it becomes turbulent, the velocity field will look much more like this. And so the boundary regions at the wall of the pipe have zero velocity, but it changes very quickly from zero velocity to mean velocity within the pipe. And so that's physically the meaning of these two regimes. And so the way in which we deal with these equations are different, because if we look at this friction factor term here, that the head loss is equal to the friction factor length over diameter v squared over 2g. If this friction factor is constant, so friction factor equals constant here, then this would be a constant, and therefore we'd have to square root our term to determine the velocity. But in case where the friction factor is proportional to Reynolds number, we can write this expression as 64 over Reynolds number. The Reynolds number is a velocity, a density, a diameter, and a viscosity. And so substituting this value into here means that you have a 1 over v term in the denominator, which cancels out with one of these velocities here. So you have a head loss which is a linear function of velocity, and therefore you don't have to square root it to find out what the velocity is. And so depending on whether you're in this laminar regime or the turbulent regime, the way you deal with the equations is slightly different. One has a square term, and one has a v to the power 1 term, and it controls how you solve the equations. We talked about a number of different types of equations. It turns out that both the expressions, I think in the midterm, the Monday and the Friday class, are type 1 problems. Type 1 problems define a velocity, so you can immediately define a Reynolds number. If you know what the Reynolds number is, you can immediately define the friction factor. And then from the friction factor, you can then use that to solve for the velocity, for the head loss in the system or the pump head within the system, by writing out the full energy equation and seeing what you're left with. And so both the expressions are type 1, so this is the sequence. You know the velocity in the fitting or the pipe. You can find the Reynolds number. If you know the Reynolds number, you can get the friction factor. And the friction factors vary in the way that we said. If it's laminar, it's a function of Reynolds number. If it's purely turbulent, it's a function not of Reynolds number. It's independent of Reynolds number. If it's a smooth pipe, then it varies along this line here. If it's a given roughness, relative roughness, then you control it based on these numbers here. These are very rough pipes. These are not very rough pipes. And you can determine the magnitude of this friction factor. Importantly, I guess, if it's high velocity, then the friction factor is a given magnitude, and it doesn't change versus the rate of flow within the pipe. So the calculations are typically maybe a little bit easier. Okay, the other thing that we did in week 9 was looking at dimensional analysis. Dimensional analysis basically says that if you have a system that is described by a number of individual variables, you can characterize a number of dimensional variables derived from these that constitute the minimum number of parameters that control the systems, the so-called pi groups. And so if you have a system which is controlled by a length dimension, a diameter, a density, a velocity, some other length, and a viscosity, the units of density would be mass per unit volume, so they include mass and length. Viscosity would be Pascal seconds, so it would include force and time. And so if you look at the number of variables you have and the number of dimensions that are represented in the system, if you take the number of variables, which is 1, 2, 3, 4, 5, and subtract the number of dimensions, mass, length, and time, we have all of them in this case, which is 3. And so 5 minus 3 gives you a total of pi groups. And so then, if you're told to, you can define some repeating variables. Repeating variables are typically defined for you so that you get a single particular answer, because you'll get different answers if you choose different repeating variables. The repeating variables are raised to the powers alpha, a, b, and c. And then the other free variables, in this case length and viscosity, are a function of these, and you can solve them in the formalism to be able to define exactly what these exponents are. Once you know what these exponents are for each of the pi groups, you end up with defining the dimensions variables. Typically, for pipe flow, for instance, these pi variables would be Reynolds number and Euler number, 2 variables. I suppose the important thing to note is that since you have these variables, pi 1 and pi 2 defined, and you only have 2 variables, then it actually doesn't need to be a straight line. You know that if you have one of these variables held constant, then it will always give a single constant number which will define this value of pi 2. So for these variables, the solution for this would be pi 2 equals constant. And so you need that to be able to solve for the system. But you'll have defined each of these variables from going through this formalism in terms of Buckingham pi. The utility of similitude is that you can define these 3 forms of similitude. Geometric similitude means that the model you're using is the same scaled down in every dimension to the prototype. So the ratios of the lengths in the 2 systems are the same. Kinematic similitude means that the Reynolds numbers between the model and the prototype are exactly the same. And dynamic similitude generally means that as a result of having these 2 being honored, then you're guaranteed that dynamic similitude is also honored. And so if you know the Euler number for the model, you can calculate the Euler number for the prototype. And so you can find out what the forces are that are applied on the prototype. But the bigger question, I guess, in these is that this diagram here, which we explained before, is that if you, for instance, have 2 pi groups, and if you hold one of these pi groups constant, then you always end up with the other pi group being defined by a single value. So in this particular case, pi 2 would be a constant. So if you know what the terms are on this equation here, you can see how they vary to keep a constant magnitude coming out of it. So you could say double the flow velocity and see what would happen to the pressure drop if that was part of, if this was an Euler number that was part of this. Anyway, so that's about it, I think. I can't think of anything else which we should talk about. So good luck. Thanks.